In this video, we're going to look at the chi-square goodness of fit test. So, first thing to consider is when should you be using the chi-square goodness of fit test? And the most common is something called a multinomial experiment. And that's an experiment where you're sort of asking one question that can occur in two or more ways. So you're looking at just one whole population and trying to see where they fall, and you're going to end up comparing expected probabilities for where you think people are going to go, or where you think these things are going to fall, and compare those to the observed data. So some examples of that would be asking a group of people at your school what their favorite movie genres are and trying to see if the probabilities at your school are consistent with probabilities across the nation. Repeatedly flipping 5 coins and counting, I don't know why I put counting the number of heads shown, trying to see if the coins behave as we would expect fair coins to behave. And you can also have the more specific type of experiment, a binomial experiment, where you do something and it happens in one of two ways. So for instance, repeatedly flipping a single coin and trying to see if it's a fair coin, so counting how many heads and how many tails you see after repeatedly flipping the coin, or looking at sort of how many times a psychic is able to correctly guess an individual's card and how many times he or she is incorrect, and compare that to random guessing. So one of the things that the chi-square goodness fit test does not do is it does not do sort of a two-way table or comparing two different groups along these. So notice I'm looking at just one group of people in the school, seeing if their probabilities match some probabilities that we are assuming. I'm looking at just these coins. If I want to consider something like seeing if male or female students have different preferences, that would be a chi-squared test for independence. And if you look in a link in the description below, I'll link to a video I've made about that. So before I go on, I'm going to point out I will have also in the description links to various portions of the video, because it's going to be a relatively long video with the examples at the end. If you'd like to skip straight to the examples, these are going to be my examples, example 1, 2, 3, and 4. But I'm going to go through and explain how to find chi-squared, how to use chi-squared, and then go through these examples. So feel free to skip around as you see fit, or skip back if you need to. So first off, how to calculate chi-squared. And what we're going to do is first collect data. So again, we're going to ask a question, and it can be I can get that result in a number of ways, and as I ask 1,000 people the same question, a certain number will answer my first choice, a certain number will answer my second choice, all the way up to my final, my kth choice in this case. Then I'm going to calculate what I expected the outcomes to be. So I'm going to take the total number and multiply by the probabilities for the first one, the probability for the second, all the way to the final probability. The null hypothesis, what we're testing, what a success is here, is that the probability that we expect matches in some way the probability, or matches the outcomes that we observed. And then, to actually find the chi-squared, we take each of our observed and subtract it off of each of the expected probabilities, square that, and divide by the expected. This sort of normalizes it. It gets it down to a consistent measure. Once we do that, how do we interpret these? Well, the first thing we do is we determine degrees of freedom and the significance level. Now, for a lot of math class problems, you'll be told what significance level, and I'm apparently doing a very poor job of I did a very poor job of this. That should be like a 1%. The degrees of freedom. So the degrees of freedom that we have here, if you think of an experiment where I have 5 possible choices. So I could have choice 1, 2, 3, 4, and 5. If I go through the probabilities, there are only going to be 4 probabilities that make a difference because the 5th one will be everything that's left over. So for instance, if each of these probabilities was 10%, so 0.1, but the probabilities of everything has to add up to 100, I don't need to be given this probability. This one will only be, or automatically be, 0.6. So if there are 5 possible choices, there are only 4 degrees of freedom. Only 4 of these are free to change. The 5th one is determined by those 4. If I am flipping a coin 100 times, if I get 63 heads, that means I get 37 tails. I don't need to know that. I'm assuming that we don't have any edges on there. So that's degrees of freedom. Significance level, you'll oftentimes be given it. I didn't stress this on the last, but what this is going to do for us, the significance level, is this tells us how unlikely it is that we are this far from our expected. The smaller the likelihood, the stronger the result. And generally, when I do a chi-squared test, I want to disprove the null hypothesis. I want to show that the coin is not a fair coin. I want to show that the people at my school have different preferences than the people than the nation. And so the smaller probability, this 5% here, actually means that there's a 5% chance, if I'm beyond this critical value, there's a 5% chance that I'm this far away, but the data still matches the expected. And 1% means that it's even less likely that I have messed up, have an error that shows me that I think I'm off, but I'm actually the same. So the smaller the percent for significance level, the stronger rejecting the null hypothesis is. And accepting the null hypothesis doesn't guarantee that it's true. It just says I'm not far enough away to make it false. And we'll see all this stuff in our examples. It'll be clear. Okay? The next thing is we can look up the critical values on a chi-squared table. So you can usually just look up one online, look in the back of a statistics book. Here's an example of a chi-squared table. Degrees of freedom are along here. Again, you choose that for this as number of possible outcomes minus 1. And the significance level is here, so a 10% significance level would be that right there. And then, if my calculated value is less than the critical value, and that means for us, let me flip back to how we calculated these. When I add up all of these, the observed were close enough to the expected to make this a small thing. So if the observed are all close to the expected, then I accept the null hypothesis that the expected probabilities are a relatively good approximation for the data, or good enough that I don't know it's wrong. If the calculated value is greater than the critical value, then I reject it. And when I do a chi-squared test, I really want to reject this because that says something a lot stronger than accepting the null hypothesis. But again, the math shows what the math shows. Just because I want something to happen doesn't mean that it has to. Now, if you're going to use a calculator, and I'm not going to show any of this stuff with the calculator, I used a calculator to do these calculations, so it's, the magic of video. I can just make it seem like I'm very quick with my computation. But if you have a calculator that does chi-squared goodness of fit, you can just look at the p-value. And the p-value, let me write this down, so the p-value is just the probability that the mean, or that's not saying means, that the observed follows the expected probability, or probabilities, but has at least this high of a chi-squared value. So I'm not going to calculate this here. It deals with an integral on the gamma function, or the not the gamma function, but the PDF for something that's gamma distribution. So but the calculator will give it to you. So you can use this without having to look up a table to show that, okay, if the probability is saying 3% and I want a 5% significance level, then I can reject the null hypothesis because I am at a less likely point than my significance level. All right, finally, let's dive into some examples so you can see how this works. So nationally, 40% of people prefer comedy movies, 25 prefer romantic, 15 prefer action, 10 prefer documentary, and 10 prefer horror movies. You ask 250 students at your school which movie genre they prefer. The results are shown in the table below. Use the chi-square test with a significance level of 5% to determine if the national statistics are a good model for your school. So we've already collected the data. It's right here. Now I need to find the expected. So this is the observed. These are the observed values. Now I want to calculate the expected. So in here, to calculate the expected, I'm going to do the probabilities multiplied by the number of students. So 250 times 0.4, and that gives me 100. Or 250 times 0.25, and that gives me 62.5. 250 times 15% gives me 37.5. And finally, for the last two, it's the same calculation. 250 times 10% is 25. So these are what I expect based on these probabilities. Now I'm going to calculate the chi-squared value. So I will do the observed minus the expected squared divided by the expected. And in this case, and I'll skip these computations shortly, but I'll just show them all for one of this. This would end up being negative 7 squared over 100. Negative 7 squared is 49. Over 100 is 0.49. And I'm going to do this calculation for all of these. So when I end up doing 57 minus 62.5 squared over 62.5, I get 0.484. When I end up doing 52 minus 37.5 squared over 37.5, I get 5.606 repeating. When I do 30 minus 25 squared divided by 25, I get 1. And when I do, finally, 18 minus 25 squared divided by 25, I get 1.96. So these are all of the values where I did observed minus expected, squared divided by expected. And now I'm going to add these up. So let me flip to some space on a new slide. So I add up all of these. I'm going to change colors, 0.49 plus 0.484 plus 5.606 repeating plus 1 plus 1.96. When I add those up, I get 9.5406 with the 6 repeating. Okay, so that's my calculated value. I know from my problem that I have, so 1, 2, 3, 4, 5 possible outcomes, which means my degrees of freedom are going to be 5 minus 1, 4. I want to use a 5% significance level, so significance I'll use is 0.05. And now I look at the table. So 4 degrees of freedom, 5% significance level, has a critical value of 9.49. So critical value 9.49. To wrap this all up, since 9.5406 repeating is bigger than the critical value of 9.49, we reject the null hypothesis, and this basically says that we believe statistically that the probabilities are different than, in this case, the national probabilities. The national probabilities are not a good model for this school. All right, second example, very similar with one slight difference. In here, they don't give you the probabilities, so I need to actually figure them out. So you have completed an experiment where you repeatedly flipped 5 coins and counted the number of heads showing. You performed this experiment 1,000 times. The results are shown in the table below. Use a chi-squared test with significance level of 1% to determine whether these coins are behaving as you would expect 5 fair coins to. All right, so in here, first off, I need to find the probabilities. And how I'm going to do that is with a little combinatorics. So I know that any of the possible outcomes is going to be 1 over 2 to the 5th, or 1 over 32. The probability of getting no, so the probability of getting no heads here is going to be, I flip the coin 5 times, I choose 0 of them, so 5 choose 0 divided by 32, which is going to be 5 choose 0 is 1, this is 1 out of 32. The probability of getting 1 heads is 5 choose 1 over 32, which is going to be 5 choose 1 is 5, 5 over 32. And I continue this way, the probability of getting 2 heads is 5 choose 2, which is going to be 10 over 32. The probability of getting 3 heads is also 10 out of 32. The probability of getting 4 heads is 5 out of 32. And the probability of getting 5 heads is 1 out of 32. Now with that, I can find the expected values. So if I do, let me make sure I'm getting these values correct. So 1 out of 32 times 1,000, this gives me 31.25. I'll put that right here. If I do 5 out of 32 times 1,000, that will give me 156.25. And I continue this. So I do 10 over 32 times 1,000 and get 312.5. Same for this, 312.5. 5 over 32 times 1,000 is 156.25. And finally, 1 over 32 times 1,000 is 31.25. Now I calculate the square differences divided by the expected. So I'm going to end up doing this process. I'm going to do the observed minus the expected squared over the expected. And when I do that, I'll get 0.002. The observed minus the expected squared over the expected. In this case, I get 0.2116. Observed minus the expected squared over the expected. And I get 0.7688. And I continue onward. So observed minus expected over the expected. And I get 0.0578. Observed minus expected squared over expected. I hope you guys are all getting the sort of pattern here. And I will get 4.2436. And finally, observed minus expected over expected. Sorry, squared over expected. And I'll get 4.05. Now I take all of these values and add them up. So I'll do 0.002 plus 0.2116 plus 0.7688 plus 0.0578 plus 4.2436 plus 4.05. When I sum all of those together, I get the calculated value of 9.3338. And now, as before, I figure out how many degrees of freedom. There are 6 possible outcomes, 0 through 5. So that means my degrees of freedom will be 6 minus 1, which is equal to 5. I want a 1% significance level, so I'm going to use a significance level of 0.01. I go to my table, 5 degrees of freedom, 0.01 significance level, and that's going to give me a critical value of 15.09. So, and I can wrap this up now. So since 9.3338 is less than 15.09, we are going to accept the null hypothesis. Basically saying that I'm not far enough off the expected values to say that it's not a good approximation. That doesn't guarantee that it is a good approximation, but I'm not far enough off to throw out the approximation. Alright, now on to some slightly simpler examples, some binomial experiments instead of multinomial. So in here, flip a coin 10 times, 6 heads, 4 tails. So I'll make the little chart. So we have heads, we have tails. 6 heads, 4 tails. This is observed. We would expect on a fair coin, being 50-50 chance for each of them to have 5 and 5. And so, to find the chi-squared, I'm going to do observed minus expected, so 6 minus 5 squared over expected, which is going to end up being 0.2, 1/5. And I'm going to do 4 minus 5 squared over 5, which will also be 0.2. The sum of all of these, so 0.2 plus 0.2, gives me a calculated value of 0.4. And now, I look for the degrees of freedom. And there are two possible outcomes, so the degrees of freedom will be 2 minus 1 equal to 1. If I know how many heads and how many total, then I automatically know how many tails there are. The significance level is 10%, so that's 0.1. And I go to my chart. 1 degree of freedom, 10% significance gives me a critical value of 2.71. So, critical value 2.71. And notice, since 0.4 is less than 2.71, we are going to accept the null hypothesis. Now, before we move to the last problem, the psychic problem, let's consider what happened. So this one looked like 60% heads, 40% tails. So you might ask yourself, well, is that always going to be the case where if I have 60% heads, 40% tails, we'll accept this null hypothesis? And the answer to that question is no. So here's a very similar problem with some slight differences. So heads, tails, 600 heads, 400 tails. This is observed. We would expect to have 500 and 500 on a fair coin. And now I can calculate the chi-squared value. It's going to be similar to before, but not the same. So I'll do 600 minus 500 squared divided by 500, which will end up equaling 20. And I'll do 400 minus 500 squared divided by 500, which will also equal 20 in this case. So my calculated value will be 20 plus 20, which is 40. But recall, we just did this, so my degrees of freedom, there are two possible outcomes. So 2 minus 1 is 1 degree of freedom. The significance level is 0.1. Back on the table, 0.1 with 1 degree of freedom is 2.71. And now we can see a very different story here. Since 40 is bigger than 2.71, since my calculated value is larger than the critical value, we will reject the null hypothesis. Basically saying that this die is almost definitely not a fair, or sorry, this coin is almost definitely not a fair coin. This probability is going to be exceptionally low. So 10% isn't a very strong statement to make, because there's a 10% chance that the chi-squared value will be 2.71 or bigger. But this is 40. You can see this is way beyond even a 1%. So we could be exceedingly confident here that this is not a fair coin. All right, last example. So we're trying to debunk a psychic. In doing this, we are going to record how many times the psychic is correct, guessing a card, and in that case also how many times it's incorrect. So we'll start with this. So observed, correct, incorrect, guessed correctly 31 times. That means that the psychic guessed incorrectly 1,969 times. Now the next thing, so this is observed, we probably need to figure out what the expected outcomes for these are. So if I'm talking about a 52 card deck, the probability for being correct is 1 out of 52, and 1 out of 52 times 2,000 gives me 38.461 approximately. Now, the probability of being incorrect is the rest, 51 out of 52. 51 out of 52 times 2,000 gives me approximately 1,961.538. So this is the expected. So you can see right away this psychic is below guessing at this point. And I'll do the same computation, so I do 31 minus 38.461 squared divided by 38.461, and that's going to be approximately 1.448. And I'm also going to do 1,969 minus 1,961.538 squared over 1,961.538, and that's going to be approximately 0.028. When I add these two together, I end up getting 1.475. And now I go through the process. So chi-squared, we have two possible outcomes, correct or incorrect. -1 means that there's 1 degree of freedom. The significance level is 5%, so I look for 0.05 on the chart. So 1 degree of freedom, 0.05, critical value is 3.84. And since 1.475 are calculated as less than our critical value, we will accept the null hypothesis. In this case, that the psychic is within the statistical bounds of just plain guessing this card, not actually having any useful knowledge here. Well, let's continue this story. So let's say the psychic didn't like our answer. So it points out that he or she correctly guessed the suit or value of the card 619 times. That seems, pretty reasonable, 1 out of every almost 3 times. So you might think, okay, let's see if that is statistically significant. So we'll do the same process. So we have correct. In this case, not correct card, but suit and or value. We have incorrect. And the observed values, in this case, were 619 correct. And 2,000 minus this, which is going to be 1,381. But now the question should be, how likely is it to actually guess the suit correct? So the probability of being correct, well, there are 13 cards in each suit and 4 cards of each value, but one of those is also in the same suit, so there are 13 plus 4 minus 1, so 16 cards that would be correct in this case out of the 52 total. And that means that the expected value here, the expected, will be found by doing 16 over 52 multiplied by 2,000, which is approximately 615.385. And On the other side, the incorrect, so probability 2, that's just the remaining. So in here, that's going to be 36 out of 52, and that means that the expected value here will be 36 out of 52 times 2,000, and that's approximately 1,384.615. So the good news for the psychic is now he or she is a little bit better than the expected, but not by much, and let's check to see if that is statistically significant. So I will do observed minus expected squared divided by the expected, and that gives me approximately 0.021, not looking good for being better than expected. And I will do, on the other end of things, 1,381 minus 1,384.615 squared, this should be an approximate, all over 1,384.615, and that will be approximately 0.009. And when I add these together, I get 0.031 approximately. And we go through the same process. Two possible outcomes, degrees of freedom, 2 minus 1. So there's 1 degree of freedom. In this case, we are still using 5% significance level. So 0.05, I go to the chart. 1 degree of freedom, 0.05, gives me a significance level of 3.84. So critical value, 3.84. And so, since 0.031 is less than 3.84, we're still going to accept the null hypothesis. It's actually exceedingly likely, exceedingly possible that the person could be completely randomly guessing and end up with this observed correct and incorrect. Alright, I hope this long video helped out. I hope it wasn't too confusing. Please feel free to comment below if you do have any questions.